Okay. So you guys will be doing the last experiment this week for, no, that was premature. Premature celebration in the front row. The last experiment on biofuels, okay? So that means that you're not going to be cheering. You're going to have another summation report. And people are going to wonder where the summation report is, and it's on page, wait, right here, page 148. Page 148 of the lab manual, okay? That is where the summation report hides out. Okay? Now I have a different computer today, and it looks like a little chunkier on the text on my computer, but up there it looks okay. All right, so that's where you'll go to do that, to do the summation report at the end of biofuels. All right, so at the end, so what we want to do is just cover the last few topics that you might need for doing biofuels, the calorimetry, a little more thermodynamics, and then I'm going to go into lecture materials on light spectroscopy, which is the subject of the last week of lab. And the last week of lab, of course, while I'll be lecturing as well, just doing a review, okay, for people that would like to come, it'd be great, and also we'll do course evaluation. So not a lot of review, we have course evaluations and everything else going on. One last announcement involves the various people that have conflict for the exam. Please make sure that you've been in contact with Linda Tiffany's arranging that, making the arrangements for the alternative exam. If you have not had any contact from Linda Tiffany, that means you didn't contact me and didn't receive contact from Linda Tiffany, and that would be bad because you would miss the exam. So please do that, okay, right away, because the space is, a concern right now, and we're trying our best. We have to know exactly the numbers. Okay, so we left off thinking about the concept of enthalpy and entropy, and enthalpy is fairly straightforward. We can perceive that sort of viscerally as heat from a reaction. Entropy is a little more abstract concept. It's a more statistical idea of representing disorder in a system. And I hope that you guys have covered that pretty in depth. And if you want to talk more about entropy with me, come to my office hours. It's an exciting topic. When you combine the two, you have free energy, and we represent that as delta G. So there's free energy, and free energy is equal to the change in enthalpy minus the temperature times the change in entropy. Okay, so you should be pretty comfortable with this definition. And it's very useful to understand the free energy of reaction, because like I said, when we were talking about disorder and entropy, you have to do work to put order into a system, correct? We all agree with that. So work is the same thing as heat. Okay, they're the same units, joules. I mean, in fact, the person who figured it out was Joule. Joule figured out that heat is work. And by just turning a crank in a device that paddled water and so forth, and the temperature of the water went up the longer he cranked. So because making order out of a disordered system requires work, that's a T delta S part. And of course, the heat change in a reaction is going to be another source of energy. You have to put the two together. You have to sum the two together to figure out the total amount of work the reaction could do, or the amount of work you'd have to do on a reaction to get it to happen in the first place. So we can think about a generic reaction like this guy, A plus B equals C plus D. And we can ask the question, well, okay, which way should this reaction go? Now, if I've made my thermodynamic measurements of H, and delta S, then delta G ultimately will tell you direction of reaction, okay? That's the point. And it'll tell you how much, if this reaction can do work, then delta G is less than 0, okay? That means it can do work, can do. And that means that C and D are favored, okay? So the reaction is going to want to go strongly toward products, okay? That means, when you have a negative free energy, that means the reaction is favorable and it will do work. Now, if the free energy is positive, then you have to do work on the system, okay? In this case, the system is A plus B to C plus D, and that would mean that under normal conditions, A and B would be favored. Okay, and this reaction is going to favor reactants. Now, this reaction will be perfectly balanced when delta G is 0, and so at that point, then the reaction cannot do work, and you don't have to have work on the reaction. It's basically essentially the reaction is balanced, and neither A, B, nor C, D are favored. Okay. So that is free energy. And just to make sure that everyone's on the same page, we can connect that back to what we learned about the equilibrium constant. Remember, the equilibrium constant is KEQ. And what about the connection between free energy? Oh, what about that? What happened? That's weird. Give me my marker back. Okay, sorry. I don't know, something happened there. Delta G equals minus RT ln KEQ. Okay? So that's the connection between free energy and equilibrium constant, okay? And as you can see, the relationship involves a logarithm term, and so numbers that are greater than 1 for KEQ are going to yield a positive number, right, for the logarithm term. We're going to multiply that by the negative sign. Because the gas constant here, this is the gas constant, that's positive. Gas constant, 8.31 joule per mole per Kelvin. And we have the temperature that's of course positive, because that's absolute temperature, by the way. So then delta G is going to be a negative number, right? So that means that when KEQ is greater than 1, delta G is less than 0, and C and D are favored, okay? So this is a really nice connection. I mean, people don't appreciate this, but another way to get at thermodynamics of reactions is, of course, to measure their equilibrium populations. And if we measure the equilibrium populations, we can get back to delta G. The other cases are pretty straightforward. If KQ is less than 1, remember KQ is a positive value, so this means a decimal value, then delta G is going to be greater than 0, because we have a negative times a negative. The log of a number less than 1 is going to be a negative number. So then A and B will be favored. And of course, the last case is where KEQ, where KEQ is equal to 1, and the reaction is balanced, okay? Which is, again, just like the case of delta G equals 0, because remember that the log of 1 is 0, okay? 0 times RT is 0. All right. So let's think about our calorimeter. Sorry, scrambled my notes. So let's look at our calorimeter. So this is kind of an interesting one. You just scroll it down. So what you guys are going to do is you're going to take your biofuel that hopefully you've synthesized some biofuel, and you're going to put it in a little container. Unfortunately, my scroll isn't so clean. Oh, there we do a cleaner scroll. I just want to leave this note there. So you're going to take some of your biofuel and you're going to put it in a little vial. Looks something like this. Okay, this is if you've read ahead in the lab manual, this is a scintillation vial. Typically used in autoradiography type experiments where you're measuring out radioactivity, but we're using it in this is a container for biofuel to create a makeshift burner. Okay, and so on the top here, you'll have a piece of aluminum foil, and you'll have a wick. It's like just a piece of rope, basically. And that wick will go down into the bottom of this thing, which will have your biofuel. Sorry, let me write this. Okay, so then you'll have some sort of ring stand contraption. Ring stand. And so you have a ring stand here, and a clamp. Sometimes this thing is, okay, something like this. And you'll have in there suspended a can, okay? Basically, it's an aluminum can. Okay, so you'll have this guy clamped onto this, there'll be a little piece of wire and so forth. And what do you imagine would be a good medium to have in the aluminum can to capture the heat from this, oh, I didn't get my orange. There we go, there's the flame. Okay, we'll make that realistic. Put some yellow in there. Okay, there we go. Biofuel's burning. And so what do you guys think you'd want to put in that aluminum can to capture this heat? Water, exactly. So there you go. Here's, of course, water's blue ever since preschool. Still is. Water. And this is a calorimeter. And the nice thing about it is, the aluminum can is nice and thin-walled. Your main heat sink here is the water, which has the same heat, nice, well-known, well-characterized heat capacity. Of course, you will figure out the device's heat capacity when you do this experiment. You'll do a calibration. In any case, this is a calorimeter, and you will be using this equation. Q is equal to the heat capacity of water times the mass of water times the change in temperature. And this heat here is going to tell you effectively the heat of combustion, okay, for your biofuel. Now to figure that out, of course, you're going to want to weigh your biofuel reaction vessel, distillation vial here, rather, burner, before and after you burn some fuel, okay? So as I asked the Wednesday lecture group, what do you think is wrong with the setup? Where do you think it's going to go wrong? Where are you going to have experimental error? Does anybody have an idea? Heat loss. So what would you do to prevent heat loss? Not use this thing. No, yeah, what you do is you put some sort of shielding around it with insulation. Okay, that would be a great strategy. That would be more like a real commercial calorimeter. Oh, did you guys notice I left out one device? What did I miss in my drawing? There you go. No one corrected me. Come on. Okay, so here's a thermometer. Clearly that's a thermometer. I'll put the little red thing in there for people that, my pens just don't change on demand. Okay, there we go. There's a real thermometer. Thermometer. Okay, yeah. So those are the main issue here is heat loss. And what you would do is you coat this with some sort of heat shield with some, say, fiberglass insulation or something like that. And you'd use materials, of course. You wouldn't use styrofoam. You'd use non-flammable materials because you have open flame there. All right, but we're not so sophisticated, unfortunately. But it's good to think about what can go wrong so you can interpret your results when you write your summation report. All right. So now we're going to talk about ultraviolet visible or UV vis light spectroscopy. And light is a very nice way to interrogate chemical reactions and looking at chemical products. It's very quick and easy. And so it's an integral part of chemistry, analytical chemistry, and spectroscopy. And so, of course, to understand light, we need to think about what is light. And light, of course, is on the electromagnetic spectrum. And, a light wave looks something like this. And remember that you'll have wavelength. The wavelength is denoted here. And you'll have amplitude, okay? Now, the wavelength is generally abbreviated lambda. And we can relate the wavelength and the frequency to the speed of light, okay? Okay, so the frequency, wavelength, and speed of light are all related. So nu here is the frequency. And speed of light is 3 times 10 to the 8th meters per second. So it's pretty fast. I think they found an Earth twin something like 500, million light years away or something like this. Yeah, how far away is it?
I don't know.
Okay. Okay. All right. Well, it's far away. But anyway, speed of light to measure how far light can travel in a light year. Obviously, it's traveling quite far in just 1 second. All right. So by using these relationships and another nice relationship, we have the energy of light. We can then see how a chemical system would be perturbed when you shine light on it. And so this relationship is where energy, or E, is equal to Planck's constant times the frequency. Okay. Planck's constant. And Planck's constant is 6.6 times 10 to the minus 34th joule seconds units, okay? So when you multiply joule seconds by frequency, which is reciprocal seconds, you will get energy in units of joules. Okay, so that means that a photon is effectively a little packet of energy, right? Makes sense, okay. So that said, as scientists, chemists, there are certain wavelengths that are easy to work with. For example, the ones you can see with your own eye. You can make characterizations of compounds just by looking at them. Of course, there are more sophisticated equipment I'll draw later, a spectrophotometer that can do this. But essentially, it's nice to know about the color range. And so UV, or ultraviolet, the wavelengths that we're talking about are under 400 nanometers, okay? And then we'll go into the violet. You can make distinctions between these colors, but roughly these ranges, green, yellow, and red. I left out orange, but I'm just giving, you can fill in the blanks here. These are approximate ranges in nanometers, okay? And so violet's around 400, 420. Blue is about 440 to 490. Green's about 490 to 570. And yellow is 585 to 620. So what you're seeing here is when you do the Roy G. Biv thing here, UV has the lowest lambda, okay? The lowest lambda. But that means because it's reciprocally related to frequency, then it's the highest energy, okay? So these are high energy on this side, and these are low energy on this side, okay? This is the spectrum here. And that's because, if you just plug this in here, if I rearrange my speed of light equation, frequency is equal to speed of light over lambda. So that means that energy is inversely related with wavelength. Okay, so it's a direct thing. It's a direct relationship between energy and frequency, and inversely related to wavelength. So how is light? How and why is light? How is light absorbed by molecules? And what you'll see, when you have a solution of say beta carotene or something to that effect, which does anybody know what color beta carotene might be? Orange, like a carrot. Orange seems to be our favorite color this class. And the reason it's orange is that it's absorbing the blue, okay? The blue, the violet, and the green, cyan part of the spectrum. And what you're left with is yellow, orange, and red. And what do yellow, orange, and red mixed together look like? Orange. So, it's not so intuitive why things are colored the way they are. You have to actually think about what they absorb, okay? And so if you're absorbing something, what do you think's happening to the energy from those photons, right? Where's the energy going? From the original, the photons are flying into this beaker that has beta carotene. You're holding up to the light, you're looking through it, and it's coming out orange. White light went in, and white light is the whole spectrum, okay? Minus some corrections for the light source for the various wavelengths. But largely, it's all the colors. And we look at it, and it looks orange. The beta carotene absorbs some of the photons. It absorbed energy. And where did the energy go? Do you guys have any idea? Yeah, you excited electrons. You did electronic transition. So let's think about that. So we have, do you remember quantum mechanics? Or your intro to it? So you have these discrete energy levels, quantized energy levels, and we have different kinds of electrons. What about the lowest level of electrons in a molecular system? Sigma bonds. We have electrons that could be in double bonds, triple bonds, pi bonds. We have electrons that are called N. Does anybody know what N means? It means non-bonding, okay? And then we have fancy orbitals that I don't know if you've had much of a chance to talk about. They're called anti-bonding orbitals. They are marked with stars. This is your pi orbital. These are your sigma orbitals. This is your non-bonding. And these are respective anti-bonding orbitals for pi and sigma, respectively. We just put a star after them. And what I've stacked up these energy levels from lowest to highest, most stable to least stable. So if we had a lowly electron down here in a pi system, and we whacked it with a photon, and I'll try to represent that. So we had a photon come in. This is my photon. That's probably not showing up. Can you see my yellow photon? All right, whatever. And then this guy gets excited and does a pi to pi star transition. Now the electron's way up here. And what happened to that photon? It was absorbed. So now instead of seeing a yellow photon, you don't see it. Okay, you don't see a yellow photon. Yellow photon vanished. Now this is not a good example for beta carotene because I said already that yellow goes right through beta carotene. But bear with me. I'll change the color here. Fine, cyan photon. So we can change color here. All right, now it's good for my beta carotene analogy. All right, so basically what you have is molecular systems are going to have pi bonds, non-bonding electrons. And just for a review, what are non-bonding electrons? You guys remember some non-bonding electrons? So I'll draw a molecular system here. Here's a molecular system. Which atom has non-bonding electrons? Oxygen. Here they are. Those are the non-bonders. Okay, it turns out that, and then who has pi? Okay, here's some pi. Here's some pi electrons here. Okay? So you need to keep track of all these things because it turns out that there are some interesting rules governing how visible light, UV visible light, is going to interact with a chromophore. A chromophore example is like this guy. Does anybody know who that is? Does anybody know this molecule? Beta carotene. This is a precursor of vitamin A. Friendly bacteria in your GI tract will turn it into vitamin A, and it comes out of carrots. There are many other chromophores.